Good afternoon, everyone. Today, we will be exploring the fascinating world of chemical bonding, part 1 of 2, which a fundamental concept in chemistry that explain how atoms combine to form compounds and material. The interactions between atoms are governed by the principle of charge, energy, and electron arrangement. At the heart of chemical bonding, we encounter various types of bond like ionic bonding and covalent bonding and etc. Without further ado, let's get into it. Chemical bonding refers to the process by which atoms or ions are held together in molecule or compound through the attractions of their electrons. This interaction occurs because atoms seek to achieve more stable electron configuration, often resembling that of noble gases. There are three main types of chemical bond. Ionic bond, which is formed when the atom transfers electron to another, resulting in oppositely charged ions that attracted each other. Covalent bond is a form when two atoms share one or more pairs of electrons to achieve stability. And metallic bond occurs between metal atoms where electrons are shared freely in a sea of electrons, allowing for conductivity and malleability. Ionic electrovalent bonding. Metals typically lose electron to become positively charged ion cation. For example, sodium loses one electron to form Na positive. Hydrogen can also lose an electron to become H positive, and even some non-metal like ammonium, NH4 positive, can form positive ions. On the other hand, non-metal usually gain electrons to form negatively charged ions. Anion, for example, chlorine, gain an electron to form Cl negative. A group of atoms like the nitrate ion NO3 negative can also have a negative charge. Elements tend to lose or gain electron to have the same electron configurations as the nearest noble gas because this arrangement is very stable. And here is what happened. When sodium reacts with chlorine to form sodium chloride, sodium loses an electron and chlorine gains that electron. Here is what happened. Na having the configurations of 2.8.1 plus chlorine 2.8.7, and it becomes Na positive, which is 2.8, plus Cl negative, which is 2.8.8. Sodium has 11 electrons, and its outcomes electron, the one in 2.8.1, is easily lost. After losing this electron, sodium becomes Na positive with the electron configurations of neon 2.8. Chlorine has 70 electrons with 7 in its outer shells, which having the configurations of 2.8.7, and it gains the electron lost by sodium, becoming chlorine negative with the electron configurations of argon 2.8.8. And this process shows how both sodium and chlorine achieve the stable electron configurations of the nearest noble gases, neon and argon, respectively. And this is some of the examples to find the charges and electron configurations from the elements listed. We have here magnesium, lithium, oxygen, aluminium, and fluorine. And for the magnesium loses 2 electrons. So in electron configuration, meaning that 2.8, the electron configurations of magnesium after losing 2 electrons is the same as neon. Lithium is L positive, which is lithium loses 1 electron, And two, when it comes to electron configurations, after losing one electron, lithium has the same electron configuration as helium. Let's look into oxygen. Oxygen gain two electrons, and in terms of the electron configuration, after gaining two electrons, oxygen has the same electron configuration as neon. Aluminium's charge on the ions happen to be aluminium loses 3 electrons, which is after losing 3 electrons, aluminium has the same electron configuration as neon, which is 2.8. And finally, we have fluorine. Fluorine and F negative charge on the ion, where fluorine gain 1 electron. And in terms of the electron configuration, after gaining 1 electron, fluorine has the same electron configuration as neon, which is 2.8. So you can refer the periodic tables of the elements on the right-hand corner to find out the charge on the ions and electron configuration. Covalent and coordinative dative bonding. Covalent bonding occurs when two atoms share electron to achieve a stable electron configuration, and both atoms contribute equally to the shared pair of electrons. Meanwhile, coordinative or dative bonding is a type of covalent bond where one atom provides both electrons for the shared pair, while the other atom does not contribute any electrons. This typically happens in complexes where a Lewis-based electron donor bonds with the lowest acid electron acceptor. Let's look into the covalent bonding and covalent coordinative dative bonding. Electrons don't move in fixed path around the nucleus like planets around the sun. Instead, they exist in regions of space around the nucleus called orbital, where there is a high chance of finding them. A covalent bond forms when atoms share electrons, and this happens when the orbital of the two atoms overlaps, and the shared electrons are attracted to both nuclei. Covalent bond can form between atoms of the same element, not just different elements, meaning molecules can be made up of atoms of the same kind sharing electrons. Dot and cross diagram. Dot and cross diagrams are commonly used to represent covalent bonding and coordinated covalent bonding, also called dative covalent bonding. And these diagrams show how electrons move when atoms form either ionic or covalent bonds. Atoms' electrons are represented by dots and the others by crosses. Although the electrons are the same, this system helps to visualize how the bonds form. In covalent bonding, atoms share electrons. Each atom contributes one electron to the shared pair, and each chlorine atom shares one electron with another chlorine atom, forming a single covalent bond, as the diagram shows on the left-hand side. Or the diagram look like this. In coordinate bonding, one atom provides both electrons in the bond. That's all for today's lesson. In conclusion, understanding chemical bonding is crucial for comprehending the behavior of matters at the molecular and atomic level. By masking concepts like dot and cross diagram, you will be able to visualize and predict the formations of compound. Thank you very much.